Hey everyone, it's Dr. Calkins. Today we're going to do some week 13, chapter 2 lecture. This takes us all the way back to chapter 2 of our original book, so it should be things that are a little easier on the eyes than things we've done, like oxidation reduction, acids and bases from those later chapters. So hopefully that's the case. I'll probably have to break this huge chapter into at least 3 parts, and we'll just go from there. Also, experiment 20, I'm going to walk you through everything that we cover in detail, step by step as well, so that's a great lab to practice everything in this chapter. So the first thing in this chapter we need to realize is that in chemistry there's lots of numbers. We just haven't used them until this part of the semester. So when you're dealing with numbers, there's 2 things to worry about: how accurate is a number and how precise is a number. In science we want both. So the easiest way to think about this is probably a target. A target has little rings and then it has a bullseye. So as you shoot arrows or bullets or whatever into the target, you make holes. And what you'd hope for is you're going to hit the target. And you hit the target again. But notice that those 2 shots, one here, one there, that's not very close to the bullseye in the middle. That means that maybe we're learning how to shoot, who knows. But that's really not precise or accurate. Accurate would be if we could hit the actual bullseye. And we did. Precise would mean that we start shooting and we get some kind of pattern. This would be precise because we're shooting in the same spot over and over. So with a number in chemistry, we'd be measuring the same number over and over and over. So these numbers should be reproducible. It means that they're very close to each other, and they should be if they are precise. But accurate means you actually hit the bullseye. So we would want these precise things to be adjusted by sights or scopes or whatever, so that eventually as we get a target, we can hit the bullseye multiple times in the center. So accurate is kind of the bullseye, that's the exact value. So that's hitting the middle. Precise is hitting the same spot. In science, we'd want to hit the bullseye multiple times, so we'd want both accuracy and precision. So hopefully that helps think about the difference between those 2 definitions you'll see in the PowerPoint. Another thing that we have to worry about with numbers is which numbers actually matter. Oftentimes in chemistry you have a calculation where you type it into your calculator and you get this entire screen full of numbers. How do we know which one of those numbers have meaning? That's a different part of the lecture, and that's an idea on significant figures. Sometimes they're called significant digits, but significant figures have several rules. One of the rules is if you're a non-zero number, you're significant. So if you read a number that's been measured by somebody else, if there's no zeros, you can just imagine that everything that you're looking at is important. You can also, by default, have zeros in between non-zero numbers. And by default, those are going to be significant because they're stuck. So the difference between those would be, say, a non-zero number would be like 230 miles to some city. So with a 0 here, that wouldn't matter. So let's say it's 236, because now we don't have any zeros in this particular example. So if we have 236 miles, we have a 2, a 3, a 6. Those are non-zero numbers. So that means we have 3 significant figures. If we had a 0 there, that would change everything. We'll see those examples coming up. If we had, say, 206 miles, notice the 0 shows up between a 2 and a 6, which are non-zeros, so it's a 0 between non-zero numbers. And there too we have 3 significant figures. So if you're surrounded by numbers that aren't 0, or if you're just a bunch of numbers that aren't 0, you're fine. And those would be easy answers. So how many sig figs do you have? Here's the issue though. If you have a 0 that shows accuracy, remember another word for accuracy is exactness. If it shows exactness, those are important. Let's say, for example, you go to the gas station and you buy 11.0 gallons of gasoline. If this number was a 0.1 or a 0.2 or a 0.9, they wouldn't charge you for 11 gallons of gasoline. They would charge you for 11.1 or 11.2 or 11.9. This number matters because it shows you how exact the gallon is, and they charge you by the tenth of a gallon. So this number could have been any number. It just happened to be coincidentally a 0 in this case. But it's showing exactness of how exact is the gallon, and it's to the nearest tenth in this case. It just happened to be a 0, not a 1 through a 9. So another way to think about this is called a trailing 0. The reason we call it a trailing 0 is because it's trailing past the decimal. So notice the decimal is here, it's trailing off to the right. So those are the zeros that we care about. Those are the ones that show us exactness. Here's the problem. So again, these are significant. And in this situation, we would have the 11 and then the 0. So there's 3 sig figs there. Here's where students get mixed up, because if you're a 0 that shows size, we would call you a leading 0 because it leads you to the decimal. Those are not significant. Those are the ones and the only ones that we need to worry about and disregard. So if you think a dinosaur bone is 65 million years old, sure, if you were winning the lottery, you would expect those zeros to be in the paycheck, but really they only show size, because if we were to convert this to scientific notation, we'd only use the 6 and the 5. Those zeros would vanish because they're only showing you where the decimal is, way down here. It's not even listed, because if it did, that would mean something else. So in this situation, we only have 2 significant figures because we only have 2 non-zero numbers. All of these zeros do go to the right, but notice they do go to where the decimal is inadvertently hidden. So this is for a large number. So it's showing you the large size, but you can also do this with concentration of acids and bases that we saw 2 weeks ago with pH calculations. You can have numbers like 0.0001, capital M is the concentration unit we saw back then. Notice these zeros are showing you to the decimal. This one's showing you to the decimal. These are showing you how small the number is. So the only number that actually matters here is this one, because that's the only number we would keep for scientific notation. So we'll teach you about scientific notation here in a minute, but for example's sake, we could just say 6.5 times 10 to the 367 power, and this was years. So notice those zeros don't show up. And the same thing here, if we go back, this would be 1 times 10 to the negative 4, capital M. Notice we don't use any of those zeros either. If we had zeros that matter, they would have been past the 1, but we didn't have any. If we would have had numbers up here that were important, they would have been past the decimal, and we didn't have any of those either. So that's how you have to worry about significant figures. If they're not zeros, we're fine. If there's zeros stuck between other numbers that aren't zeros, we're fine. If they show exactness after the decimal, so if we were to put a 0 here, that would count 2. Now we'd have 2 significant figures. But notice it has to be after the numbers, not going to the decimal or to the decimal, even though the decimal is not being shown. So watch out for those. So numbers matter, and with significant figures, when they matter is when we do problems. So let's show you those 2 examples, and then this lecture will be done with. So when we deal with problems, we have to deal with PEMDAS, order of operations. So notice in PEMDAS we need parentheses, exponents, multiplication, division, addition, subtraction. And multiplication and division, notice that rule will trump the addition, subtraction. And in simplest terms, when we're looking for multiplication and division problems, we want fewest significant figures in our answer. Addition, subtraction will be fewest decimal places. So really, in all reality, what we're going to be worried about is this rule here, because addition, subtraction is going to be minimal in our particular chapter. So say if we try an example of where this can come into play, Let's try a multiplication division kind of problem. Fewest significant figures. So if we take a number like 41.0 and we times it by 2.0, notice these zeros matter. So we're comparing 3 significant figures to only 2 significant figures. 2 is fewer, and 2 is going to limit our answer. We type this into our calculator, and this could have been inches and inches, doesn't really matter what the unit is in this early in this chapter. But when we multiply this, we would get, say, 82 inches squared in our calculator, which is 41 times 2. And we get lucky in this case because the 8 and the 2 is also 2 significant figures. If for some reason it was 82.0, that would be 3 significant figures. That is more accurate than this particular number, has more, actually it's a bad word for that, but has more significant figures, has more significance. So we want to watch out for that 0 and make sure that it didn't show up. So be careful. These zeros, sometimes they're needed, sometimes they're not needed. Just depends on the problem. But in this case, we're choosing fewest significant figures when given the option. So you'll see that a lot in experiment 20 for practicing in the homework. If we're in addition subtraction, it'd be like saying we add 1,000 to 100 to 10 to 1. When we do this, what's important is not the math problem itself. The issue that we have with numbers like this is we don't know where they stop because of those zeros. It wouldn't really change if we were to add a 0 here, or a 0, 0 here, or a 0, 0 here. The answer would still be 0, 0, 0. So we don't worry about significant figures at all in this situation because we can have numbers of various sizes. But what matters here is when did the answer stop? This one stops at the ones place, tenths place, hundreds place, and thousands place. We have no idea what the numbers are here, here, and here, maybe here and here, or here. And since we don't know what these numbers are, that would change the answer. So we can only give an answer in our homework. Our calculator would do all this for us, and these numbers could be whatever. But we have to stop where the decimal stops. The decimal stopped for this number in particular because these numbers weren't known. And if they weren't known, we can't assume the answers of any of these values have any meaning. We would just use them for rounding. So the answer we'd be looking for is the one that stops at the same decimal as our weakest, most uncertain number, and that's 1,000 that we assume it be to the ones place. In our situation here, if these zeros weren't exactly known, we could even stop it there, but it really just depends. So maybe one more example of this difference, and then we'll stop. So let's just say we have 123.0, we have 2.01, and then we have a 3.006. So when we add or subtract these, doesn't matter. We get a 6, a 1, a 0. 5 and 3 makes 8. 128. Calculator can do it as well. So this is what our calculator would say. If we circle this, we might get that warm fuzzy feeling inside when it matches something in our homework. If we circle it, we still get it wrong. Why? Well, remember, if the numbers stop here, the answer stops here. Everything else determines rounding, and that's what we want in our calculator. So stop where the numbers stop. That's what we mean by fewest decimals. Stop at the tenths place because we don't know what was here, we don't know what was here, we don't know what was here. Since we don't know, we can't guess. If these were 8s or 9s, that would change everything. So be careful, stop your numbers where your weakest number was stopped, and that's addition subtraction. But remember, if it were multiplication division, if we have, say, 22, and then we had, say, 1.01, when we multiply. So when we do this, you get, 22.22. So if we did this in our calculator, and we get this answer, you might think very quickly that I don't know how to circle this because it's what my calculator says. The problem is, and this should scare you, we have two significant figures in 22 because they're both non-zero numbers. This zero is trapped in between, so it has 3. But our calculator gave us 4 numbers that look significant, and that should be something that scares you. Because the answer is either in 2 or 3, not 4. Sometimes your calculator screen can be entirely full of numbers. That's even worse. We need to know when to stop, but the rule says fewest significant figures. 2 is fewer than 3, so stop your answer at 2. Use everything else for rounding, and the answer here is still 22. So that's how multiplication and division work. Division worked the same way, we just did do one of those problems. It'd be tougher for me to do those in my head, that kind of idea. So hopefully this gives you a better understanding of how to deal with numbers. The only thing that we didn't mention was scientific notation, so maybe briefly I'll mention that to you. But again, that's something that most students are more than capable of doing. So as we look at something like this, just remember that if we have a number like 1,000, we're going to convert that into scientific notation. You just move the decimal 1, 2, 3 positions. That would be 1 times 10 to the 3rd power. If it was a small number like 0.001, we would move it to the right. That would be 1 times 10 to the negative 3rd power. So you would have saw that a lot with the acid-base kinds of ideas already. When you take a number out of scientific notation should always have a number in front that is significant, and then some exponent that shows you the sign. So if we were to add or take away zeros, those would be the ones that wouldn't matter in the first place. Those would have been leading zeros. So let's just say we have a number like 1.01 times 10 to the 5th power. Well, if you have 1.01, just move it 5 spaces to the right. 1, 2, 3, 4, 5. Those would now be zeros. So if you throw in a 0 here and here and here, you get 101,000. Notice these zeros showed size. They weren't important. It's these numbers that were important. So even if we were to go backwards, this would be positive 1 power, positive 2, positive 3, positive 4, positive 5 power that we would have saw in the answer. So you can always check your work for these, which is nice. If you had a small number like 1.00 times 10 to the negative, let's say 7, that would have been something we would have saw, say, for acid-base concentrations from neutral. This was very accurate because it has 2 trailing zeros that are important. That's why they're kept in scientific notation. Here, because it's a negative, we need to make this a small number, so move back 1, 2, 3, 4, 5, 6, and 7. Each one of those, running out of room, would be a 0. So 0.123, 4, 5, 6. Now we have that 1, 0, 0. Notice these are trailing. Those are the ones that are important. These were the ones that were not. So stay away from these zeros. These are the ones that are leading you to the decimal. Pay attention to these zeros because these are the ones that are trailing away. And that kind of summarizes those issues. Leading zeros are lost in scientific notation, but those trailing zeros are kept. And that'll be it for this lecture.